So now we're going to look at specific types of mechanical waves. And perhaps one of the simplest ones is if you take a piece of string and you disturb one end, you get a propagation along the string, and that's going to be a wave on a string. And in fact, you may have even done this when you were a kid if you ever used a piece of string and tied two tin cans together, and if you yell into one tin can loud enough, it actually causes vibrations to go down the string, and you can hear them in the other tin can as they get converted back into sound waves. So let's have a look at that system and apply Newton's second law to it to figure out how these waves propagate and what they look like from a physics point of view.
So what we've got here is, imagine we've got a string with some low amplitude wave on it. And what we've done is we've taken a small piece of the string and we're zooming it up to give us this picture here. Now the string is going to have a tension that runs through it, and we're going to allow it to have a mass. So we're going to define rho as the mass per unit length of the string. So if you like, you can think of it as a one-dimensional density. So because there's a mass here, it means that the tensions at the two ends do not necessarily have to be equal. Now, the other approximation we're going to make is we're going to assume that we have a small amplitude wave. And so what this means is that phi1 and phi2 are both small. So the first thing we're going to do is we're going to apply Newton's second law, and we're going to apply it in the direction that the wave propagates. So what we've got is we've got the wave propagating in this direction. So we're also going to assume that this is a pure transverse wave. So we have pure transverse wave. And what that means is there is no motion of the string in the left-right direction. And so in this case, if we look at Newton's second law in the left-right direction, it means that there must be zero net force. And so what that means is that T1 cosine phi1, because we want the component in this direction here, and so we're closing the angle, so it's T1 cosine phi1, must equal, and again we want the component in this direction here, so we're closing the angle and projecting down onto the x-axis, so that must equal T2 cosine phi2. Now, if you have cosine of theta and theta is small, then cosine of theta is roughly equal to 1. In fact, it's 1 minus theta squared over 2, but plus order of theta to the fourth. But for small values of theta, this term here is negligible, and so we say that cosine theta is roughly equal to 1. So what that means is that we've got these two quantities here are both going to be equal to one another. We've got T1 is equal to T2, or should I say roughly equal to T2, and so we'll say that this is equal to a common tension T that runs through the string. So this, of course, is only going to be true for a small amplitude wave. So now let's apply Newton's second law in the other direction. So now we're applying it in the transverse direction. So now what we have is we have the net force is equal to mass times acceleration. Well, the net force now is going to be T2 sine phi2. That's in the positive direction here. So T2 sine phi2 minus T1 sine phi1, and that's going to be equal to the mass. Well, the mass of this element here is going to be the mass per unit length multiplied by the length of the element, and the length of the element here is just delta x. So the mass here is just rho delta x. This is the mass. And then the acceleration. Well, the acceleration is going to be equal to the rate of change, the second derivative of the rate of change of position with respect to time at this point in x, right? So I want to know what is this is its y coordinate here, and we are at position x here. And the reason I've written it as a partial derivative is that y is a function of x and time, and I'm wanting to know what the rate of change of position is for a particular value of x. So effectively my acceleration is a function of position, because each point on the string here is going to be accelerating at a different rate. It's not necessarily going to accelerate, the whole string is not accelerating at the same rate independent of position. And so here what I'm doing is I want the rate of change of y with respect to time for a constant position in x. And so that is now a partial derivative, and since I want the acceleration, not the velocity, it's the second derivative. So it's d2y by dt squared for a constant value of x. So this is why it's a partial derivative and not a true derivative. So now I've got two equations. I've got this equation here, we'll call that 1, and I've got this equation here, and we'll call that 2. So what I'm going to do is I'm going to take 2 and I'm going to divide it by the tension T, remembering that T here is roughly equal to T1 and T2, which is equal to T1 cos phi 1 and T2 cos phi 2, right? Because cosine of phi 1 and phi 2 for small amplitude is roughly 1. So these two things here are roughly equal to the tension. So let's divide these two equations. So here are the two equations that we have. We got this, remember, from Newton's second law in the transverse direction, and this came from Newton's second law in the same direction as the wave. And here's our diagram in the corner to remind you of what we were doing. So what I'm going to do is I'm going to take this and I'm going to divide it by the equation below, and as you can see, the way I've written it out here, each of these three terms here are roughly equal to one another for a small amplitude, and so I'm going to divide this term by this term by this term, and this term by this term, since they're all roughly equal. So what that gives me is it's going to give me T2 sine phi 2 divided by T2 cosine phi 2 minus T1 sine phi 1 over T1 cosine phi 1, and that is going to be equal to rho over T times delta x partial squared y by partial t squared. So I've taken this equation here and I've divided it by these terms here, which are all roughly equal to one another, but I've chosen to use this term when I'm dividing this term, I've chosen to use this term when I'm dividing that term, and I've chosen to use t here, the common tension in the string, when I'm dividing the acceleration term. Now, the reason for those choices is now pretty obvious, because here the t2's cancel and the t1's cancel, and so what I have is I have tangent of phi 2 minus the tangent of phi 1 is equal to rho over t times delta x partial squared y by partial t squared. Now, if I look at the tangent of phi 2 here, well, the tangent of phi 2, if I have this is the string, this is the angle it makes with the x-axis at this point here. So this is going to be x, and this is now x plus delta x. So at phi 2, where this is phi 2, what I have is this is delta y, this is delta x, and the tangent of phi 2 is equal to delta y over delta x, and if I take the limit that delta x goes to 0, this becomes now partial y by partial x, because I'm looking at a constant point in time, and y, remember, is a function of position and time. So I'm looking at a tangent of phi 2 here is just partial y by partial x, and I'm looking at the position x plus delta x. So this is x plus delta x. So similarly, I can calculate the tangent of phi 1. That's at this point here. This is just going to be partial y by partial x at constant time and at position x. So this difference here I can rewrite as partial y by partial x at x plus delta x minus partial y by partial x at x. Okay, so I'm now going to rewrite this equation a little bit more, and I'm going to keep the terms here. So I'm going to have rho over the tension times partial squared y by partial t squared, and this is equal to 1 over delta x times partial y by partial x at x plus delta x minus partial y by partial x at x. And so the last thing I'm going to do is I'm going to take the limit as this delta x. So in other words, I'm going to shrink the size of this element, take the limit as delta x goes to 0. And this of rho over t times partial squared y by partial t squared. And this now is going to be partial by partial x of partial y by partial x, because this is just the delta of partial y by partial x, right? This here is just, if you like, delta of partial y by partial x, and I've got delta of this divided by delta x in the limit that delta x goes to 0, and so this just becomes the differential again. And so what I'm left with is that rho over t times partial squared y by partial t squared is partial squared y by partial x squared. And that is a wave equation. And what it gives me is it gives me that the speed, remember, it's 1 over, this is 1 over c squared here, so the phase velocity, the wave speed, is the square root of t divided by rho, where t is the tension in the string and rho is the mass per unit length. So this is the mass per length, and this is the tension. So now we have our wave equation. We have a prediction that the wave speed will increase with tension and it will decrease with mass per unit length.
So now we've derived the wave equation for waves on a string. And we've seen that the phase velocity of these waves depends on the tension in the string and depends on the density or the mass per unit length of the string. So let's have a look at a couple of different strings under different tensions to see if that bears out in a qualitative fashion. Okay, so here we have a metal spring that's going to act as our string. We're going to do a transverse wave on it, and because it's metal, it's got a relatively high mass per unit length. So at the moment we've got it under low tension, so let's see how the waves move on it. And so we can see the waves moving on this system. So now we're going to increase the tension. So now we've got the same spring under a higher tension. Let's see how fast the waves move on this. And you can see that they move quite a bit faster than they did under the low tension. So, and here's low tension again. right? So clearly the wave speed increases when we increase the tension. So this is our high mass per unit length. Now let's look at a rubber string where we're going to have a low mass per unit length. So this is now a rubber hose that we're going to use as our string, and we're going to show you it under low tension. Oops. And you can see that the wave moves quite a bit faster than it did for the low tension for the steel spring. And so here we've got a low mass per unit length, and so even with low tension, we're still getting quite a high wave speed. Now, if we tension the rubber, we've now got a higher tension, and we've got a low mass per unit length, and in fact, it may be so fast that you will hardly see it at all. In fact, it is so high that you can hardly see any wave move at all because the wave speed now is so incredibly fast. So we've seen in a qualitative fashion how the wave speed agrees with our predictions. Increasing tension increases the speed of the wave, and increasing the mass per unit length decreases the speed of the wave. So we've now seen how waves on a string work. We've shown that the result we got was consistent with what we observed when we did those qualitative experiments. And next, though, one of the most important applications of waves is the transmission of energy and information. So let's have a look at the power transmission of a wave on a string.
What we want to do is calculate the power transmitted by this wave on a string. So the wave is moving in this direction, as we can see here. So the power that's transmitted by the wave, if we consider this little element here, is going to be the work that the wave does on this element, and that's going to be purely due to this force at this end of the element. So the power transmitted by the wave must be the power of this force. Well, the power of the force is the force in the direction of motion multiplied by the velocity. Well, this is a purely transverse wave, so we have a velocity v here in the y direction, so the power of this force is going to be the y component of the tension multiplied by the velocity. Now the displacement of the string y is a function of both x and t. And the velocity is going to be the rate of change of y with respect to time, but because it's a function of both x and t, we need a partial derivative because we're interested in the velocity at a particular value of x, that being the value of x for this particular element here. So our velocity is a partial derivative of y with respect to time given a constant value of x. Next, we want to calculate the y component of the tension. So let's have a look at that. Here's our tension vector, and it makes an angle theta to the horizontal. And so what we've got here is we've got a change in x, and we've got a change in y, but the change in y, of course, is in the negative direction. So we can say that the tangent of theta here is equal to, in the limit that delta x goes to 0, is equal to minus partial y by partial x. So here what we're doing is we're looking at the rate of change of y with respect to x at a constant point in time, right? We're taking a snapshot image of the string, and we want to know the gradient of the string at that value of time. And so we have this minus sign in here because it's acting, this is a negative change in y here. So what that means is that partial y by partial x is equal to minus tan theta. And if we look at this here, and instead of thinking of it as the slope of the string, we look at it in terms of the tension vector here, then this is going to be the x component of tension, and this is going to be the y component of tension. So this is equal to minus ty over tx. Now, if you remember back to when we were talking about this being a small amplitude vibration when we derived the wave equation for the wave on the string, then we had that Tx here was roughly equal to the tension on the string. And so we can rewrite this equation here as minus Ty over T. So if we rearrange this, this gives us now that ty is equal to minus t partial y by partial x. And so we can now substitute this into our function for the expression for the power. And so this gives us that the power is equal to ty, which is minus t partial y by partial x, times now the velocity, which is partial y by partial t. So we've got an expression for the power now. Next thing we want to do is we want to evaluate these partial derivatives, and so we can actually get it in terms of quantities that we can easily measure. So let's do that. So here's the expression for the power that we just derived, and what I've done here is I've written down the displacement of the string as a function of position and time, and I've used the solution for our wave equation. So I'm going to use this to calculate these two partial differential quantities here and then come up with an expression for the wave power. So first of all, I want to differentiate this with respect to x. So partial y by partial x is going to be, well, I'm going to have a minus sign from cosine going to sine, and then I'm going to have a plus k because I'm differentiating with respect to x, keeping t constant. So I'm going to have ka and then sine kx minus omega t plus phi. Now for partial y by partial t, I'm doing the same thing here. I get a minus from cosine going to sine, and then I have a minus omega. So this becomes plus omega a, and then sine kx minus omega t plus phi. So what I'm going to do now is I'm going to take these two expressions here and I'm going to substitute them in to this expression for the power. And so I now have that the wave power is going to be minus t times, well, I've got minus ka here, so that goes plus. So ka, and then I've got an omega a here, so I'm going to have an omega, I'm going to have an a squared, and I'm going to have an omega in here, and then I'm going to have a sine squared kx minus omega t plus phi. So this is my expression for the power. Now I can just do a quick sanity check here. Power has to be positive because otherwise it would mean that power was being transmitted in the opposite direction to the way the wave was moving. And sine squared here goes between 0 and 1, and all of these quantities are going to be positive, so that's good. The power, although it varies, is going to remain constant, is going to remain positive. So, okay, now I've got this expression for the power. The next thing I want to do, though, is simplify it a little bit. So I'm going to go back to our expression for the phase velocity. So we have c is equal to f times lambda. Now, we know that 2 pi times the frequency is equal to our angular frequency omega. That was from our definition of angular frequency. And we know that our wave number k is equal to 2 pi over lambda. So if I substitute these two things back into our expression for the phase velocity, what I have is I have that the phase velocity here is equal to, well, the 2 pi's are going to cancel out because I'm going to have an omega over 2 pi here, and I'm going to have a 2 pi over k. So what I'm going to end up with is I'm going to end up with omega over k. So if I, now what I want to do is I want to express this omega times k in terms of, I want to get it in terms of c and omega. So if I look at this here, what I'm going to have is I've got k is equal to omega over c, so that means that omega times k is going to be equal to omega squared over c. So I can use this now to rewrite my power for the wave as t times omega squared over c multiplied by a squared and then sine squared kx minus omega t plus phi. But the phase velocity for a wave on a string, remember, is equal to the square root of t over rho. So if I look at t divided by c, this is going to be t multiplied by the square root of rho over t. So this is just going to be equal to the square root of t times rho, where remember rho is the mass per unit length. So the power transmission of my wave on a string I can now write as the square root of t times rho times omega squared a squared sine squared kx minus omega t plus phi. And this is the expression for the power transmission of a wave on a string. And so one of the things to note here is that for a constant tension and a constant mass per unit length, the power doesn't only just go as the square of the amplitude, it also goes as the square of the frequency. So a higher frequency wave transmits power faster, has a higher power transmission. The other thing to note is that our power transmission is not constant. It varies both as a function of position and as a function of time. So let's have a look at calculating a mean power transmission for the wave. So here's our expression for the power transmission of a wave, and if we look at that and we try and plot it, then here's our power. And here's, let's look at a constant position, and so we'll just look at how it varies with time. What we find is that we end up with a sine squared function, which I'm drawing really badly here. And it varies between this value here, which is going to be the square root of t times rho times omega squared a squared, and 0 here for when sine squared is 0, and this is when sine squared is equal to 1. So the average value, since this is a symmetrically varying between 1 and 0, the average value is just a half. So if this is 1 and this is 0, the average value of sine squared, so this is the mean value of a sine squared or a cosine squared function. So what this means is that if the mean value of this is going to be a half, then we have the mean value of the power transmitted by the wave is just a half times the square root of the tension times the mass per unit length times omega squared a squared. And so often this is the quantity that you want because we're not interested in the instantaneous power transmission of a wave at a particular position or instant in time. What we're usually more interested in is the mean power transmission rate of a wave. And so this is the mean power transmission for a wave on a string.
So we've seen now how the power of a wave on a string depends on the amplitude of the wave, and the larger the amplitude, the larger the power of the wave. But a wave on a string is only a one-dimensional wave. It cannot spread out, it just has to transmit information and energy along the length of the string, and so its amplitude, if there's no damping forces, will remain constant as it moves along the string. But most of the waves we encounter in everyday life are two-dimensional and three-dimensional waves. The ripples on the surface of a pond is an example of a two-dimensional wave. The sound waves I'm speaking to you with, and in fact the light waves that you're seeing me with, are both examples of three-dimensional waves that spread out from a point, if you have a point source, in a sphere around that source. So in the next video, we'll have a look at an example of a mechanical wave that exists in 3 dimensions, the acoustic wave.